In Module 19, we have studied the structure of the oxygen carrier hemoglobin. Carrying that forward, we will learn about the functioning of hemoglobin in this module. After studying this module, you shall be able to know the structure of dioxygen binding site in hemoglobin, understand the importance of polypeptide chain in hemoglobin, understand what cooperativity is and the molecular basis of cooperativity, learn about the oxygen dissociation curve and Hill plot for hemoglobin. We have already learnt in Module 19 that hemoglobin is a tetramer with 4 subunits. Each subunit of hemoglobin contains a single molecule of heme and a polypeptide chain, also referred to as the globin. Heme is Ferrous protoporphyrin complex. In hemoglobin, the coordination number of Ferrous is 5 with a square pyramidal geometry. Ferrous is coordinated to the 4 nitrogens from the tetrapyrrole ring system and 1 imidazole nitrogen from the histidine residue of the polypeptide chain as shown in the figure. The histidine is called the proximal histidine and is residue 92 of the beta polypeptide chain and residue 87 of the alpha polypeptide chain of hemoglobin. The 2 sides of the heme plane are called the proximal side and the distal side. Proximal side has the proximal histidine. Side of the heme plane at which exchangeable ligands abound is called the distal side. In deoxyhemoglobin, it is vacant. However, the distal side has a histidine residue called the distal histidine, which is near the heme but not bound to it. It makes the 6th coordination site of deoxyhemoglobin accessible to only small molecules. Protons present in the heme cavity weaken the ferrous oxygen bond in oxyhemoglobin. Distal histidine, being a basic amino acid, binds the proton present in the heme cavity via upsilon nitrogen and liberates them on the other side via the delta nitrogen. Ferrous ion in deoxyhemoglobin is in high spin. High spin ferrous has a size of 78 picometer and is larger in size than the heme cavity and therefore lies approximately 40 picometer out of the heme plane towards the proximal side, giving a dome shape to the heme. Dioxygen molecule binds reversibly to ferrous with the iron oxygen-oxygen bond angle of 120 degrees. This binding brings about conformational changes in the hemoglobin. The spin state of ferrous changes from high spin to low spin, resulting in a concomitant decrease in the size of ferrous to 61 picometer. The ferrous now fits beautifully in the heme cavity. As it slips into the heme cavity, it also pulls the proximal histidine towards the heme plane. Thus, ferrous is hexa-coordinated in oxyhemoglobin with an octahedral geometry as shown in the figure. Oxygen is hydrogen bonded to the imidazole NH of the distal histidine. A thought comes to the mind. Why has nature made the structure of hemoglobin so complex? Since oxygen coordinates to ferrous of heme, can't iron 2 porphyrins without the protein chain act as oxygen carriers? The answer is no. The reason being, naked heme, that is iron 2 porphyrin without the protein chain, reacts irreversibly with the dioxygen in an aqueous environment. Let us look at the figure to understand the detailed mechanism. As soon as naked heme binds dioxygen, it combines irreversibly with another naked heme, forming the mu peroxodimer having iron 3. This peroxodimer reacts with another heme to give the oxo-bridge dimer called hemetin. Hemetin is unable to transport dioxygen. The globin, besides acting as a carrier of heme in hemoglobin, also plays a role in stabilizing the heme-oxygen complex so that the oxidation of ferrous of heme does not take place, and it can act as an effective dioxygen carrier. The polypeptide chains alpha and beta are folded in such a manner that the hydrophobic or the water-repelling amino acid residues are inside and most polar residues are on the outside. These hydrophobic residues form a non-polar or hydrophobic pocket in which heme is present. The polypeptide chain prevents the irreversible dioxygen oxidation of ferrous in two ways. Firstly, for the oxidation of ferrous to ferric, the simultaneous presence of oxygen and one or more molecules of water is required. The amino acid residues in the heme pocket have hydrocarbon groups, that is, non-polar groups. They provide a hydrocarbon environment of low dielectric constant and so act as a non-polar solvent, extruding the water molecules out of the heme pocket, thus preventing the oxidation of ferrous. Secondly, because of the presence of polypeptide chain, the formation of mu-oxo-heme dimer becomes sterically unfavorable. Let us now try to understand the electronic state of iron and dioxygen in oxyhemoglobin. The molecule of oxyhemoglobin is found to have a zero magnetic moment and no unpaired electrons. To explain this observed magnetic behavior, two hypotheses have been proposed. First hypothesis, proposed by Pauling and Correll in 1936, explained the diamagnetic character of oxyhemoglobin by proposing the presence of low spin ferrous and coordinated singlet dioxygen. Low spin ferrous in an octahedral environment has an electronic configuration T2G6 Eg0, making it diamagnetic. Singlet oxygen is also diamagnetic. The second hypothesis was given by Weiss in 1964. He proposed that oxyhemoglobin has a low spin ferric and a superoxide radical anion. They are formed by transfer of an electron from ferrous to triplet oxygen, that is 3O2. Strong antiferromagnetic coupling between the low spin ferric and the superoxide radical anion results in the observed diamagnetism at room temperature. One of the most important features of hemoglobin is cooperative dioxygen binding. One hemoglobin molecule can bind to a maximum of 4 dioxygens as shown. K1, K2, K3 and K4 are the stepwise formation constants for the binding of dioxygen to hemoglobin molecule. The magnitude of these formation constants follow the order K1 is less than K2 is less than K3 is less than K4. That is, the binding of the first dioxygen is the most difficult and the fourth dioxygen is bound most readily and tightly, or in other words, we can say that binding of a dioxygen to a molecule of hemoglobin enhances the binding of additional dioxygens to the same hemoglobin molecule. Similarly, removal of one dioxygen from a molecule of hemoglobin makes the removal of other dioxygens easier. This effect is seen in many proteins and is called the cooperative effect. There is a relationship between the partial pressure of dioxygen in the blood and the saturation of hemoglobin molecule with oxygen. This relationship is clearly depicted by the oxyhemoglobin dissociation curve. Oxygen dissociation curve or oxygen saturation curve is a plot of percentage saturation with dioxygen versus the partial pressure of dioxygen. For hemoglobin, the dissociation curve is sigmoidal in shape. As seen in the figure, at low partial pressures of dioxygen, hemoglobin does not bind dioxygen effectively. At high partial pressures of dioxygen, hemoglobin has high percentage saturation with dioxygen. There is a plateau area at high partial pressures where increasing level of PO2 will not yield much in terms of the saturation with dioxygen. The oxyhemoglobin curve helps in understanding how blood carries dioxygen from the lungs to the tissues. At the lungs, where the partial pressure of dioxygen is high, hemoglobin is saturated with dioxygen. In tissues, the partial pressure of dioxygen is low. The affinity of hemoglobin for dioxygen is low, and it releases the bound dioxygen. Let us now try to understand how to quantify cooperative effect. The Hill coefficient is used to provide a quantitative measure of cooperativity of ligand binding. It is usually estimated graphically from a Hill plot. It was originally formulated by Archibald Hill in 1910 to describe the sigmoidal dioxygen binding curve of hemoglobin. Mathematically, we can arrive at the Hill equation. We can describe the binding of dioxygen to hemoglobin by the equilibrium Hb plus NO2 giving HbO2n. The equilibrium constant for the binding beta is the concentration of oxyhemoglobin divided by the concentration of hemoglobin and the concentration of uncombined oxygen. The saturation Y is defined as the ratio of concentration of oxyhemoglobin to the total hemoglobin concentration. The total hemoglobin concentration is the sum of concentration of deoxyhemoglobin and oxyhemoglobin. By substituting and rearranging, we get the expression for Y as Y is equal to beta concentration of O2 to the power n divided by 1 plus beta concentration of O2 to the power n. As O2 is a gas, it is convenient to express concentration in terms of partial pressures of oxygen, that is PO2. Replacing the concentration of oxygen by PO2, we get Y is equal to beta PO2 to the power n divided by 1 plus beta PO2 to the power n. And therefore, 1 minus Y is equal to 1 divided by 1 plus beta PO2 to the power n. Dividing Y and 1 minus Y, we get Y divided by 1 minus Y is equal to beta PO2 to the power n. This equation is called the Hill equation. Taking log of both the sides, we end up getting log Y divided by 1 minus Y is equal to log beta plus n log PO2. A plot of log Y by 1 minus Y versus log PO2 is called the Hill plot. Its slope n is called the Hill coefficient. It is a measure of degree of cooperative binding. If the slope is greater than 1, it indicates positive cooperativity. That is, once one ligand molecule is bound to the protein, its affinity for other ligand molecules increases. If the slope is equal to 1, it indicates no cooperativity. That is, the affinity of the protein for a ligand molecule is not dependent on whether or not other ligand molecules are already bound. If, however, the slope is less than 1, we have negative cooperativity. That is, once one ligand molecule is bound to the protein, its affinity for other ligand molecules decreases. Negative cooperativity is very rare. The degree of cooperativity increases with the value of N. For hemoglobin, Hill coefficient has a value of approximately 2.8. This shows that the binding of oxygen in hemoglobin shows positive cooperativity. If oxygen had bound independently to the 4 heme units of hemoglobin, N would have a value of nearly 1. We have till now seen what is cooperativity and how do we quantify cooperativity. Now let us look into the molecular basis of positive cooperativity of hemoglobin. We know that hemoglobin is a protein with a quaternary structure. It can exist in 2 quaternary states, namely the tense or the T state and the relaxed or the R state. The conformations of the individual polypeptide chains and their relative orientations are different in the T and the R states. Oxygenation rotates the alpha-1 beta-1 dimer in relation to the alpha-2 beta-2 dimer about 15 degrees. When hemoglobin switches from the T state to the R state, alpha-1 and alpha-2 globins move closer to each other. Similarly, beta-1 and beta-2 globins move closer in the R state. These 2 states are in equilibrium with each other. Dioxygen can bind to hemoglobin in both the states. However, it has a higher affinity for hemoglobin in the R state. Deoxyhemoglobin is constrained by salt links or electrostatic interactions between the polypeptide chains of the 4 heme subunits. There are 8 such salt links, 2 between the beta units, 4 between the alpha units, and 1 each between alpha and beta. A trigger mechanism proposed by Ferrous explains the basis for cooperativity in hemoglobin. On oxygenation, ferrous ion changes from high spin to low spin, becomes smaller in size and is able to fit in the heme cavity. As it is bound to the proximal histidine, it also pulls the proximal histidine towards the plane of the heme ring. This movement of proximal histidine leads to a change in the tertiary structure of the polypeptide chain of the subunit. These conformational changes lead to the rupture of the salt links between the subunits. Strain in the hemoglobin molecule gets reduced, and this encourages the binding of dioxygen to the iron of the second heme unit, which in turn encourages the binding of dioxygen to the third and the fourth heme unit. This sequential increase in dioxygen affinity gives rise to the sigmoidal shaped dioxygen dissociation curve for hemoglobin. Let us now summarize what we have learnt in this module. The coordination number of ferrous in oxyhemoglobin is 6, with ferrous being coordinated to the 4 nitrogens of the tetrapyrrole ring, a histidine residue from the polypeptide chain and dioxygen. In deoxyhemoglobin, the dioxygen binding site is vacant. The distal histidine, although not bound to ferrous, has an important role to play. It makes the 6th coordination site of deoxyhemoglobin accessible to only small molecules and also shuttles protons away from the dioxygen binding site. The polypeptide chain present in hemoglobin prevents the irreversible oxidation of ferrous. Oxyhemoglobin has zero magnetic moment and no unpaired electrons. This can be explained by the presence of low spin ferrous and singlet oxygen as proposed by Pauling and Coriel, or low spin ferric and superoxide radical anion as proposed by Weiss. The binding of dioxygen to a molecule of hemoglobin enhances the binding of additional dioxygens to the same hemoglobin molecule. This cooperative effect is explained by the trigger mechanism. Cooperative effect is responsible for the sigmoidal shaped dioxygen dissociation curve for hemoglobin and the value of approximately 2.8 in the Hill plot for hemoglobin.